On behalf of Indira Gandhi National Open University, we welcome you for this video lecture session. I am Subhasis Maji, Professor in School of Engineering and Technology of Indira Gandhi National Open University. Today's topic is different forms of stored energy and specific heat. This is the 8th module of the course Thermodynamics and its applications. So, dear learners, after listening to this video lecture, you will be able to know that energy is a property of a system. You will be able to understand the concept of different forms of stored energy. You will be able to describe the other modes of energy. You will be able to explain the conservation of mass. You will be able to know the specific heat at constant volume, also the specific heat at constant pressure, and lastly, you will be able to discuss the energy of an isolated system. My dear friend, let us first discuss about the concept of control mass. We call it closed system. Here we shall discuss all the conservation statements for a control mass. Thus, we are considering the mass within a boundary surface which can undergo translation, rotation and deformation, but no mass cross the boundary. This is very important point. We have to note that no mass will cross the boundary either from system to surroundings or from surrounding to system. First of all, let us discuss that energy is a property of a system. Let us consider a system which starts from state 1 to state 2 by following the path A. So it will follow the path A, start from state 1 and reach at state 2 and returns from state 2 to state 1 by following the path B as shown in the figure. So the system undergoes a cyclic process because it starts from state 1 following the path A reaching the state 2, and in the return it starts from state 2 and following the path B to reach at state 1. So for path A we can write the expression for the first law of thermodynamics, that is QA is equal to del EA plus WA, that we call it equation number 1, and for path B we are again writing the expression for energy equations, that is QB is equal to delta EB plus WB, that we call it equation 2. Now for a cyclic process we know that sum of the heat input is equal to the summation of the work. So for a cyclic process we can write QA plus QB is equal to WA plus WB. So we can rearrange these equations and write that QA minus WA is equal to WB minus QB. So we can write delta EA is equal to minus delta EB, because from equation 1 delta EA is nothing but QA minus WA, and from equation 2 we can say that minus delta EB is equal to WB minus QB. So we can write that from the expressions, that is delta EA is equal to minus delta V. So similarly we can get for the path C that if we consider the path C, that means starting from state 1 following the path A reaching at point B. After that, you start from state 2 and reaching at state 1 following the path C. So we can write down the expression which we have got earlier, the similar expressions we will get, that is delta EA is equal to minus delta EC. So once you are getting delta EA is equal to minus delta EB, another one you are getting the same kind of expressions as delta EA is equal to minus delta EC. So from these two equations you can say that delta EB is equal to delta EC. So from here you see that the change in energy for the path B is equal to the same change of energy at path C. That means energy is a point function. So energy is a property of the system. Therefore, it is seen that the change in energy is independent of the path followed. So energy is a point function and hence energy is a property of the system. Now let us discuss about different forms of stored energy. In thermodynamics, energy can be in two forms: energy in transit, energy in storage. So work and heat interactions are the forms of energy in transit. Observed at the boundary of the system, they are not the properties of the system. Energy in storage, called internal energy, is a point function and a property of a system. But work and heat are not the point function, they are path functions. So work and heat are not the property of the system, but energy, pressure, temperature, these are all point functions and these are the properties of the system. Dear learners, let us discuss about the different forms of stored energy. There are two modes in which energy can be stored in a system. First one is macroscopic energy mode and the second one is microscopic energy mode. Macroscopic energy includes the macroscopic kinetic energy and potential energy, whereas microscopic energy includes internal energy. So macroscopic kinetic energy is expressed as half mv square, where m is the mass and v is the velocity, and macroscopic potential energy can be expressed as mgh, where m is the mass, g is acceleration due to gravity and z is the datum heat. Internal energy is intimately related to the internal structure of the substances in terms of the internal microscopic energy mode. Now let us discuss about the specific heat at constant volume. Let us consider the change in internal energy for a substance where U is the internal energy, is a function of temperature and specific volume. So we write mathematical expressions like U is equal to U within bracket T and V. That means U is a function of temperature and specific volume. So here T and V are known as the independent variables and U is known as the dependent variables. So the value of U we can find out if we know the two independent properties like temperature and specific volume. Now if U is a function of temperature and specific volume, so total differentiation du we can write dou U by dou T at constant volume multiplied by dt plus dou U by dou V at constant volume dV. But the change in internal energy per degree of temperature change for a constant volume process is this first derivative and is called the specific heat at constant volume. Cv is equal to dou U by dou T at constant volume. So we can, from this expression, the first partial derivative, that is dou U by dou T at constant volume, is known as the specific heat at constant volume
and this is a very important term in thermodynamics. Next, let us discuss about the specific heat at constant pressure. We will proceed in the same way as we have discussed for the internal energy, but there internal energy we have taken as a functions of temperature and specific volume, but here enthalpy will be taken as a functions of temperature and pressure. If the change in enthalpy is required, then this is considered in the same manner as the internal energy for a substances, where H is equal to H is a function of temperature and pressure. So if you take the total differentiation of enthalpy, that is dH is equal to dou H by dou T at constant volume multiplied by dt plus dou H by dou T at constant pressure dP. So for a constant pressure process, the first partial derivative is significant, that is dou H by dou T at constant volume. This property is the specific heat at constant pressure, defined as Cp is equal to dou H by dou T at constant pressure. So we have understood what is specific heat at constant volume. Specific heat at constant volume is dou U by dou T at constant pressure, whereas the specific heat at constant pressure, that is Cp, we are getting dou H by dou T at constant pressure. So these two specific heats are very important while analyzing any thermodynamic process. Now let us discuss the first law of thermodynamics for some elementary processes. For a constant volume process, then let us see what will be the expressions for first law of thermodynamics we get. So for the first law of thermodynamics, we know that du is equal to dq minus dw, but for a constant volume process, the work done is zero because volume is not changing. So du is equal to dq. So the change in internal energy is equal to the change in heat supplied. Now let us discuss about the constant pressure process. So we know that dw is equal to pdv. So the first law of thermodynamics is du is equal to dq minus dw. Put the value of dw, that is equal to p dv. So we get du is equal to dq minus p dv. So dq is equal to du plus p dv. Now since the pressure is constant, so we can write d within bracket u plus pv. Now u plus pv, that this combination of these two terms will come so frequently while analyzing the thermodynamic processes. We call it is equal to enthalpy. So enthalpy H is equal to U plus PV. So dQ is equal to dH. So for a constant pressure process, the change in heat supplied is equal to the change in enthalpy. Now let us discuss about the adiabatic process. For adiabatic process, dQ is equal to 0. So if we start from the first law of thermodynamics for energy equation, that is du is equal to dq minus dw, but for adiabatic process dq is equal to 0. So if you put dq is equal to 0 in the energy equation, we get du is equal to minus dw. So this is the expression for change in internal energy equal to minus dw for adiabatic process. There are other modes of energy. We have encountered three modes of energy till now. One is gravitational potential energy, other one is kinetic energy, and the third one is internal energy. But there are other modes of energy. Some examples are chemical energy, strain energy, electrical energy, magnetic energy, and nuclear energy. Chemical energy: during a chemical reaction, reactants are converted into products. For example, when petrol vapor and air burn to form carbon dioxide, water vapor, and other combination products in a petrol engine, this may be accompanied by heat and work interactions and changes in properties such as temperature and pressure. But you see that when you burn coal, then we get tremendous heat. In boiler, the water is transformed into high pressure, high temperature steam because of the heat which we get by burning of coal. So chemical energy stored in coal, we can get heat energy by burning of the coal. Strain energy, a compressed spring or elastic structure has part of its energy in the form of strain energy. Same thing is for electrical energy. A system comprising electrically charged elements is said to have part of its energy in the form of electrical energy. Now you know very well that electrical energy is very much required in our day-to-day life. Without electrical energy, we cannot survive. Magnetic energy. A system comprising of magnetic pole has part of its energy in the form of magnetic energy. And nuclear energy. Nuclear power is the use of nuclear reaction that releases nuclear energy to generate heat, which most frequently is then used in steam turbine to produce electricity in a nuclear power plant. There are two types of nuclear reactions. One is nuclear fission, another one is nuclear fusion. Now, for nuclear fission, nuclear energy originates from the splitting of uranium atoms, a process called fission. This generates heat to produce steam, which is used in a nuclear power plant to generate electricity. Nuclear fusion. The nuclear fusion is a reaction in which two or more atomic nuclei combine to form one or more different atomic nuclei. Now, for nuclear fission or nuclear fusion, so initial mass of the reactants will be lesser than the final mass of the final products. Now there is a mass defect, but that mass will be converted into energy with the help of, we know that Einstein's famous equation, that is E is equal to mc square. So if there is a mass defect due to the nuclear reaction, that mass will be converted into heat energy. The law of conservation of energy of an isolated system. The energy of a system remains constant if the system is isolated from its surroundings as regards heat and work. For an isolated system, dq is equal to 0 and dw is equal to 0. So from first law of thermodynamics, that is equal to dE is equal to dq minus dw, but dE is 0 since for an isolated system dq is equal to 0, dw is equal to 0. So we say that change in energy is 0 for an isolated system. So the energy of an isolated system is always constant. Dear learners, let us discuss the law of conservation of energy of an isolated system. The energy of a system remains constant if the system is isolated from its surroundings as regards heat and work. For an isolated system, dq is equal to 0 and dw is also equal to 0. From the first law of thermodynamics, dE is equal to dq minus dw. So dE is equal to 0 because dq is 0 and dw is also 0. So if dE is equal to 0, then we can say E is constant. The energy of an isolated system is always constant. Now let us discuss about function representation, because while analyzing any thermodynamic process, we must have the knowledge of some mathematics about, we must know about the implicit function, explicit function, we should know about how a function is represented and what are dependent variable, what is independent variable. So preliminary knowledge of mathematics is absolutely necessary for analyzing any thermodynamic process. So let us consider this function, that is f within bracket x, y, z is equal to 0. So this function actually represents the surface in three-dimensional space coordinates. This type of function is known as implicit function or surface. The dependent and independent variables are not directly indicated. However, if it is represented as z is equal to function of x and y, then it is known as explicit function. Here z is dependent variable and x and y are known as independent variable. So if z is a function of x and y, if it is written as z is equal to functions of x and y, so the value of z depends on the values of x and y. So x and y are known as independent variable and z is known as dependent variable because the value of z depends on the value of x and y. Now let us try to solve exercise 1. A function is represented as P is equal to C T divided by V, where P is the pressure, T is the temperature, and V is volume, and C is constant. Question is this an implicit or explicit representation? What are the dependent and independent variables? Since this function P is equal to T C T divided by V, P is equal to C T divided by V, so it is given in terms of explicit form. So this is an explicit representation. Here the value of P depends on T and V, so T and V are independent variables and P is dependent variables, and of course this is an explicit representation. Now exercise number 2, the properties of a certain fluid are related as follows, that is U is equal to 196 plus 0.718 T, PV is given as 0.287 within bracket T plus 273, where U is the specific internal energy in kilojoule per kg, T is in degree centigrade, P is pressure in kilonewton per meter square, and V is the specific volume in meter cube per kg. Determine Cp and Cv. Now we have already discussed the expression for U, that is here U is given as 196 plus 0.718 T, but if you want to calculate the specific heat at constant value, that constant volume, that is nothing but dou U by dou T. So if you differentiate the first equation, that is U is equal to 196 plus 0.718 T, if you differentiate U with respect to T, then you will get the value of Cv. Now while calculating Cp, we must have the expression for H, but H is equal to U plus Pv. U is given, Pv is given. You can easily find out the value of H. Now dou H by dou T will give you the specific heat at constant pressure, that is Cp. Now let us see how we have calculated these values, that is Cp and Cv. So U is equal to 196 plus 0.718 T. PV is given as 0.287 within bracket T plus 273. So Cv is equal to du by dt is equal to 0.718, unit is kilojoule per kgK, and H is given as U plus PV, and Cp is equal to dH by dt is equal to 1.0 kilojoule per kgK. Exercise number 3. The specific heat at constant pressure of certain system is a function of temperature only and may be expressed as Cp is equal to 0.5 plus 10 within bracket T plus 100 joule per kgK unit, where T is the temperature of the systems in degrees centigrade. The system is heated while it is maintained under a pressure of 1 atmosphere until its volume increases from 2000 cc, that is cubic centimeter, to 2400 cc and temperature 0.0 degree centigrade to 100 degree centigrade. We have to calculate how much heat is added to the system, how much does the internal energy of the system increases, assuming the mass of the system as 1 kg. Now we have got the expression for Cp, so we can calculate the value of H from these expressions, because initial temperature is 0 degree centigrade, final temperature is 100 degree centigrade. Now let us see how we can proceed for this exercise. For a constant pressure process, del Q is equal to dH is equal to mdH. So H is the small h is the specific enthalpy and Cp is equal to dH by dt. So dH is equal to Cp dt, but expression for Cp is given. So we get the expression for dH is equal to within bracket 0.5 plus 10 divided by T plus 100 and dt. Now if we integrate these equations, we can calculate the value of del H. That comes out to be 0.5 T plus 10 log within bracket T plus 100 bracket close, and upper limit is 0 and lower limit is 100. So if you put the upper limit as well as lower limit for these expressions for calculating delta H, so that equation comes out to be delta H is equal to 0.5 into 100, because T you will get 100 minus 0, that is 100, plus 10 log 200 by 100, and mass is given as 1 kg. So Q12 is equal to del H equal to 56.931 joules. Now if you want to calculate the work done from state 1 to state 2, that is integral of P dV, since it is a constant pressure process, so P within bracket V2 minus V1, so V2 is given as 2400 cc, V1 is given as 2000 cc, and it is an atmospheric pressure that is equal to 1.01325 into 10 to the power 5. And if you put the value of P as well as V and V1 and V2, we will get W12, that is work done from state 1 to state 2, comes out to be 40.53 Newton meter. So from first law of thermodynamics, we know that Q minus W is equal to du. So increase in internal energy is equal to Q minus W. Q you have already got, W you have already calculated. Finally, you can calculate the increase in internal energy is equal to 16.40 joules. Now let us quickly discuss for this objective type questions. Select the correct answer. Thermodynamic properties are the macroscopic coordinates significantly only for the systems existing in the states. 4 options are given: thermal equilibrium, mechanical equilibrium, chemical equilibrium and thermodynamic equilibrium. Of course, the final answer is D, that is thermodynamic equilibrium. Next question is it is not a point function. The 4 options are given: temperature, pressure, energy, power. So temperature is a property, pressure is the property, entropy is the property. These are all point function. So answer obviously will be option 4, that is power. Next question is the cyclic integral of this is 0. Work transfer, heat transfer, temperature and latent heat. Now work, heat and latent heat, these are all path functions. So only thing, the temperature, that is a property, and for a cyclic integral of temperature S0. So C is the correct answer. And next objective question is heat transfer to a closed stationary system at constant volume is equal to work transfer, increase in internal energy, increase in enthalpy, increase in Gibbs equation. Obviously the answer is B, that is increase in internal energy. Let us summarize our discussions. We have discussed the concept of different forms of stored energy. We have discussed the conservation of mass. We have discussed the specific heat at constant volume and also the specific heat at constant pressure. We have discussed the energy of an isolated system. We have also discussed the other modes of energy, and finally we discussed energy, a property of the system. And for all these things we have discussed in detail. Lastly, we have solved some numericals so that whatever we have discussed you can apply for solving the numericals related to the first law of thermodynamics, whether it is control mass or control volume. Here we are finishing our today's discussion. So in the next class we will come with a new module. Thank you very much.